Hello and welcome to the Sky Night Magazine vodcast. This month I'm in Llandudno in North Wales for the National Astronomy Meeting 2011. Over the course of the next couple of minutes we'll be hearing from some of the UK's top astronomers about the research that they're working on and also getting an update from some of the biggest space observatories. Last year I visited the Chorbolton Observatory in Hampshire to see the construction of part of the LOFAR radio telescope array. At the National Astronomy Meeting, I spoke to Dr. Karen Masters from the University of Portsmouth about the first science results from LOFAR and what types of objects it observes.
Well, LOFAR stands for the Low Frequency Array. It's a telescope that works at the lowest frequencies that are accessible from the surface of the Earth. We actually have two bands. We work just below and just above the FM radio band. These spindly antennas you can see reflected in the sunglasses here, they're the low band antennas, and then the black boxes are the high band antennas. LOFAR can look at a wide variety of things, anything basically that emits low frequency radio waves. One of the key science projects is to look for the time when the first stars turned on in the universe. They create a sort of a phase change in the universe. They change it from being mostly neutral hydrogen, which does emit low frequency radio waves, well, at least once you consider the redshift radio waves that LOFAR can detect, to the universe being mostly ionised hydrogen, which doesn't emit that radio waves. And so LOFAR is hoping to detect that step change in the frequency. But LOFAR can do many other things. We're looking at pulsars, observations of the sun, even some SETI. First science results from LOFAR, we're looking at pulsars, the most sensitive observations of pulsars that have ever been taken. And what was fun about those observations were that LOFAR observed 5 different pulsars at the same time. Because LOFAR has no moving parts, pointing the telescope is done by introducing time delays between when the signal is sort of recorded from each antenna. If you imagine, if you look straight up, the signal from the pulsar would reach each antenna at the same time. But if you looked at something over on the horizon, it would reach the antennas on that side a little bit before the ones on the other side of the array. So we point the telescope by introducing these time delays. That means you can use the same data with slightly different time delays to point in different directions all at the same time. LOFAR, once it's finished, will have 36 stations in the Netherlands, plus 5 international stations is the current plan. Right now we have 27 Dutch stations working, and the 5 international stations are up and running, not always fully integrated with the array. The stations, the hardware itself is quite simple. You saw us installing the one in Chorbolton with volunteer labour. The parts themselves are very simple. What makes LOFAR such a powerful telescope and such a unique sort of pathfinder for the next generation of radio telescopes is that we have 5,000 of these antennas spread across Europe, and we connect them with high-speed internet, making use of fibre optics, to a supercomputer in Groningen in the Netherlands, which runs LOFAR. And it's that sort of technology of high-speed internet and supercomputing that allows LOFAR to be such a powerful telescope.
The James Webb Space Telescope is billed as the successor to Hubble. It will study the farthest reaches of the universe at infrared wavelengths, looking at everything from the formation and evolution of galaxies to the birth of planetary systems. I asked Professor Ian Robson, Director of the UK Astronomy Technology Centre, about the UK's involvement in the mission.
UK has a very heavy involvement in the mission. Of the 4 instruments, one of them, the MIRI instrument, the Mid-Infrared Imaging Spectrometer, that's got a UK PI from the UK ATC, Professor Gillian Wright, and she sort of herds a whole bunch of consortia across Europe to produce the MIRI instrument, and that currently is at the Rutherford Appleton Lab. It's being tested for its final testing before it will deliver to NASA to await launch on JWST. The instrument, it's a very complex imager, spectrometer and a coronagraph, and it has to be packaged from, normally this thing would be a couple of cubic meters in volume. It has to be really shoehorned into an incredibly small space, so there's over 200 reflecting surfaces and lots of detectors and complex optics, and it all has to sort of survive launch. It also has to keep on working when it's cooled, and so fundamentally it's a huge piece of engineering technology to drive that, and it's a fabulous piece of work.
Also represented at the National Astronomy Meeting was the European Space Agency's Planck mission. I asked Dr. Mike Peel from Jodrell Banks Centre for Astrophysics about what sort of telescope Planck is.
So Planck is a fairly unusual telescope in that it's got two mirrors in it. It's got a primary mirror and then a secondary mirror which reflects light onto the focal plane in the centre. The reason for this is it wants very low side lobes, so light coming in from the side of the telescope going onto the detectors, because it wants to make very careful observations of what it's seeing. The whole satellite actually rotates at once every minute, so it scans out a circle across the whole of the sky. So Planck will deliver a full sky map of the whole of the universe at very high frequencies, radio frequencies, between 30 gigahertz and 857 gigahertz. So between about 3 times higher than your satellite TV up to 80 times that. CMB, it's a cosmic microwave background. It's the light that's left over from the very early universe. So you can think of the start of the universe kind of like a fog, where everything was really, really compact, really dense. And if you were in that kind of environment, you wouldn't be able to see very far. Light just couldn't travel. And then as the universe expanded outwards with the Big Bang, then it got to a certain point where suddenly photons could travel. The fog lifted. And you can see right the way back to that time using Planck and even using something like your own TV, you see some noise which is coming from the very early universe. It's uniform everywhere across the sky. You have to look at very small bits of it very accurately to be able to find anisotropies, so bumps in this, where it's not quite smooth. And that is a signature of the early universe. It's telling us what was in that time when it was foggy and you got waves bouncing around in that epoch. So using that you can then measure how much mass there is in the universe, what kind of scales the structures are on, a lot of very interesting properties about the universe as a whole. We haven't released anything from the CMB yet. What we have released is information about the foregrounds of Planck. So all of the stuff from our galaxy, which gets in the way of looking at the CMB, we've started looking at some of the science that you can do with that.
The UK is also involved in the Herschel Space Observatory. I spoke to Professor Matt Griffin from Cardiff University about the telescope and its special construction.
Well, Herschel is a telescope that works in the far infrared part of the spectrum, most of which is completely inaccessible from the ground because the Earth's atmosphere, especially water vapor, absorbs most of the radiation. So we need to go into space to have access to this part of the spectrum, and it's very important because if we observe at these wavelengths, which are a couple of hundred times longer than the wavelength of visible light, then we can see into the large clouds of gas and dust in which stars are born in our own galaxy, and we can also look at distant galaxies and see how they formed and evolved. So Herschel allows us to see the birth processes of stars nearby and in the distant universe.
It has quite a large mirror, doesn't it?
Yes, it's 3.5 meters in diameter, and that's the largest space telescope ever launched by quite a way. So it's considerably bigger than the previous infrared mission, NASA's Spitzer mission. And that bigger telescope gives us better image quality and allows us to see finer detail. Although it's big for space, it's important to remember that the Herschel mirror is actually small by the standards of ground-based telescopes. We're not yet at the stage where we can launch a huge mirror 10 or 15 meters in diameter into space. Maybe that's something for the future.
You've got this amazing model of the spacecraft itself here at NAM. What's the big black object underneath the mirror there?
Well, this is a 1:4 scale model of Herschel. So there's the primary mirror at the top and the secondary mirror. And in this large tank, which is a liquid helium cryostat, basically a souped up thermos flask, are 3 scientific instruments. They sit just inside at the top there, and they're kept very cold by liquid helium because they don't work at all unless they're at very low temperatures. So this tank contains enough helium for Herschel to operate for about 3 years, and it's more or less halfway through its operational lifetime at the moment. When all the helium in this tank has boiled off, then the Herschel mission will end because none of the instruments will work. So we have to do a lot of concentrated science in those 3 years and make sure we don't waste a single day.
What sort of objects has Herschel been looking at recently?
Well, Herschel is a very versatile observatory. So as I said, it works well in studying star formation. So star formation in our own galaxy is one of the big themes of Herschel. And Herschel is doing surveys of large areas of the sky, particularly the galactic plane, to investigate the interstellar medium, the clouds from which stars are born, and to look deep within the clouds at particular objects where star formation is active today. In addition to that, it's looking at very distant galaxies, which we can't see in such great detail, but we can measure their properties statistically.
Well, that's it from me here in North Wales at the National Astronomy Meeting 2011. I hope you've enjoyed this look at one of the UK's biggest astronomy conferences. Clear skies, and I'll see you again next time.